Thank you. Good morning. So today we'll talk about a particular case study on, we name it electronic inclusion for users with SSMI. Here SSMI stands for severe speech and motor impairment. So in this talk, we will briefly talk about one of our research project going for last 3.5 years with a school called Vidyasagar in Chennai, or earlier it was known as the Spastic Society of India. And this school catered needs of students who has uh, severe motor impairment, and also in addition they cannot talk, and most of the students they have cerebral palsy, and but they also take care of students who has learning disability or visual impairment or so on, but we mostly worked with these students with cerebral palsy. So our aim was engaging these users with society because they cannot speak, they cannot move their different body parts like hand or legs, and their engagement with the rest part of the society is very limited through their parents or caretakers. And saying so, it doesn't mean that they are have any cognitive deficiency, like their range of cognitive ability is also wide, but many of them, if not all, has cognitive ability of uh, they are able-bodied counterpart of similar age group, and they come to Vidyasagar for learning. So Vidyasagar was not only a rehabilitation center, and it was not a medical facility, rather it was a school where the students were coming to learn, and they were in different classes. So they follow a open schooling standard, and they are in different levels of classes, and they could follow classes. So the second bigger aim was that making information technology accessible to them. So we can now presently we are very much tied up with information technology, like this online lecturing, our social networking, our online news indexes. So we tried, and many of these information technology is provided through electronic means like smartphones, computers, etc. And although they have access to this electronic technology, but it was not accessible to them, and many times they couldn't afford to buy a very costly assistive technology from abroad, mostly Western world. So we try to see that whether we can make a cost-effective solution for them. And we taught them, I guess, controlled interaction techniques. So in the next slide, we will again tell you in more detail that why we um, suddenly tuned on IGS controlled interaction, because we found that they were already using non-electronic means of IGS controlled communication. So we tried to use the electronic means and try to help there in both education and entertainment. And finally, we also try to foster social inclusion through electronic social networking, because they always talk to some other person, even their peers, through their caretaker or parents or teachers. And we try to see that if we can make a direct communication channel among them. So if we can take a step back towards the broader domain of accessible computing. So common ways dividing people based on their range of abilities, or rather impairment, like there is a screen reader for blind, and screen magnifier, high contrast display for other visual impairment who lacks visual acuity or contrast sensitivity. For motor impaired users, there is a sticky key scanning system, brain computer interface. And for specifically for users, such users who has severe speech and motor impairment, a class of software is developed called augmentative and alternative communication aid, which aims to speak out their mind. That it's not like mind reading, rather they try to construct sentences using an electronic virtual keyboard or storyboard sort of electronic user interface, and the system speak it out like normal communication. So if any of you have ever attended any lecture by late Professor Stephen Hawking, you can see an example of such system. And later on, these systems are also enhanced to let such people use other computer softwares like spreadsheets, PowerPoint presentations, etc. But many times we noted that dividing uh, any assistive technology or accessible interface using the type of impairment of user is not very useful. So why I'm saying so, what happens that I again borrowed this particular picture from one Austrian professor. I met him a really long time ago in 2009, but I still think that this picture is still really valid, that there lies the user, and he needs some sort of say different service, and it need not to be categorically a so-called disabled person. It can be a pilot, as we saw in the 2 weeks ago in lectures, that when someone is driving a car, or someone is flying an aircraft, or someone just simply walking and try to send a text message over his mobile phone, he is also have some traits of typical what is typically we attribute as a disabled person, and we rather use a term called situational impairment. That means the situation makes the person impaired, although he is not categorized as a disabled people. So saying so, here lies the user, and here lies a whole gamut of assistive technology, accessible device, etc. And there is a gap between the two. So the user do not know which will be the best form of accessible technology for him. And even if he get one, say something for visual impaired user, then that may not cater for his say maybe slight lack in range of abilities of his hands or legs. And what we noted, why we particularly look or we are looking at this SSMI user, because the cerebral palsy is, as you may know, that it is a issue with the brain, and since the brain gets affected, it affects their vision, their sometimes their cognition, and of course their motor action. So if I divide the same person into three parts, that this technology for motor impaired, this technology for blind or visually impaired, it will not work for them. So rather we go for a more inclusive approach, in which we, instead of a point to point solution, we rather make a more generalized solution which covers different range of abilities. And you will see in the following slides that how we are achieving that. So when we are talking about these users with motor impairment, so traditionally they use computing system using a particular technique called scanning technique, or rather more specifically single switch scanning techniques, although scanning techniques can also be available as a two switch version. So what does it mean? That since they cannot move many of their body parts, they can hit a single push button switch, and the whole computer interface is made accessible to them by a single switch press. This switch can be attached to their head, their leg, their upper leg portion, or to their arm or their palm, in whatever body portion they are most suitable with. And even this switching can also come through a, say, blink type of action, although that is difficult to use. But I mean, a single input channel to the computer instead of a continuous mouse or keyboard interface. And how we make the computing system accessible, that we progressively highlight different section of the screen, and we kind of iteratively reach the desired button. So here, for example, on the left screen and right screen, say I want to click the right red colored button. So this is one example of such scanning system, where we are dividing the screen into 4 segments, and we are selecting our desired segment when it is turning green. And this size of these rectangles are getting smaller and smaller. And finally, after the third iteration, I can select the target, and now I am moving to another button. Okay, and I am pressing a switch when my desired portion is turning green, and I am pressing the switch maybe second time to confirm it, that I do not make a wrong selection, like that. So as some of you can, if you think about the maths, you can see that we can do many different things in terms of this division of blocks, that why 4, why not more, or how we can reduce the iterations. And in fact, there are a lot of mathematics can go there by which we can optimize this number of division and number of iteration. And this is the same thing in a different way. So this the second thing is I invented. I termed it as cluster canning system. So what it does, that it automatically cluster the screen elements based on their spatial position, and instead of blindly dividing the screen, which often has a lot of blank space, it only uh, put the, or it only consider the screen region where there is a target there, and the result is we can reach the desired button in much less iterations than the traditional block scanning system. But whatever we use, as you can see that for selecting a single button, I have to press the single switch 3 or 4 times, and it turns out to be a pretty slow technique. But still saying so, a lot of assistive technology for users with severe motor impairment still depends on single switch scanning technique. So moving on, when we looked at our end users at this Vidyasagar, we saw that uh, we try to classify them based on the existing scales of motor impairment. These scales are like gross motor function classification, manual ability classification, communication function classification, and all of these scales has 5 levels. The 5 is the worst, that means the most limited range of abilities, or 1 is the able body. And we found that in all these scales, this particular bunch of users at the highest end, that means they are very severely impaired. And how they communicate, so on the right side of the screen here you can see some of their communication chart, like it's handwritten ABC, etc. This is also a keyboard printed out. So one of their parents or teachers or caretakers hold this chart in front of them, and this person manually try to analyze where they are looking at, and by analyzing their eye gaze manually, they try to say that interpret what the person is trying to say. And believe it or not, this is the way they also write their exams, that they got a question and someone hold a chart in front of them, and they try to look at a particular answer, and someone has to write it on their behalf. And the overall process is time consuming, but this is what the best they can do. So then, as I was telling at the start of the, before the start of the lecture, that initially as engineers we went there and we went with a bunch of software which I also previously worked with, and they couldn't use it. So then we rather took a step back, and instead of just providing them a software or hardware solution, we try to analyze their ocular parameters, that what is going wrong, that these guys, we are trying to use their eye gaze to use a software interface, and I can use it, my students can use it, but this person cannot use it. What is going wrong? So we give them a very simple study. We make a complete black screen and make a small white square into the black screen, and this white square is coming at random position in the whole screen. And we just told them that whenever you will see a white square on the screen, you just try to look at that white square. And we control the duration of the white square, how long it will be visible on the screen. And we ran these studies for both able-bodied people and to these users with SSMI. And what we noted, that when they are trying to fixate their attention on the white dot, they are trying to do that, but there is a lot of unwanted eye gaze movement, which is visible through these histograms. This is the offset calculation. So offset means that, say I am telling you to look at 100, 100 pixel, but you are looking at say 200 and 200 pixels. So the X offset will be 100 and Y offset will also be 100. So when we make a histogram of this offset, we found for able-bodied user, the peak is at 0 or between plus 50 minus 50 pixels. For this users with SSMI also, the offset is, I mean, the peak is at plus 50 minus 50. But you can see this, the height of this blue bar is less than the orange bar in both cases. And the spread is much higher for the users with SSMI. That means when, even though they are trying to fixate attention at a point, their fixation is moving all across the screen. And this particular condition is known as nystagmus, and later when we looked at literature, we found that that is also a manifestation of cerebral palsy, which has already been found in clinical studies. But for these users, when someone we design user interface, we often do not take care of that, and this is come from again this wrong approach of thinking that this guy is motor impaired, so give him motor impaired solution. So many times designers do not think that the human is a single person, and he may have a combination of range of abilities. Next, what we did, that we tried to analyze their eye movement patterns. So again, we gave them something like a game interface. So we told them that wherever you will look at the screen, it will turn green. If you look longer, it will gradually turn yellow, and then it will turn red. So we develop the software accordingly, and we tell them that you paint the whole screen as much as you can. So here on the right hand side, you can see a pattern by a able-bodied user that the whole screen is red and yellow. And this is a pattern by user with SSMI. And here are two more such example. And we get such snapshot, 26 of such snapshots from 11 or 12 users. And in most of them, we find that they cannot look at all different portions of the screen equally like their able-bodied counterparts. And almost in more than 90% cases, this top left portion of the screen remains blank. That while we try to put screen element or populate a screen from top left, and then we make a left to right scan and top to bottom scan, but for these users, fixating attention at the top left of the screen is difficult, and it is not for one user. It is we collected data from 11 or 12 users. So that means certainly there is something difference happening in even the eye movement patterns, not only on the fixation pattern. Then we developed another game in which, again, it was kind of like a game that we show them picture of 10 balloons on the screen. So 1, 2, 3, all these boxes were a balloon. And we told them that if you fixate attention at the balloon will blast and disappear. And you try to make all these 10 balloons disappear. So that happens to be a very popular game among them. So many of them wanted to play it multiple times, and that generated a lot of data for us. So in that, we analyze that how they are selecting these balloons to blast, and which balloon they are first trying to blast, and how long they are taking to blast this balloon one by one. And here you can see in this picture that for these users with cerebral palsy, they mostly start at the center of the screen, and then they were going like left and then right here, and they found this bottom portions difficult. And in this balloon also, you can see that we didn't keep anything on the top left. While for able-bodied user, you can see a clear left to right and top to bottom scan, that people try to blast the balloons from this way and then they come down this way. So that also indicated us that their visual search pattern, instead of this top to left and top to bottom and left to right scan pattern, they rather try to look at the middle portion of the screen and then radially search the screen. So with that knowledge, one of our PhD students, Jivita, she actually designed a simple word construction game. So the game was simple. On the right hand side of the screen, you can see the video that we show them a picture like say home, or a simple 3 or 4 letter words based on the contemporary education level. And in one condition, what we did, that we told them you have to construct the correct word by choosing the letters. And we also made sure that they know the letters, like there is no learning problem, that they know that how to spell home. In one condition, what we did, that we put all these letters HOME at random positions of screen. In another case, we put them at their preferred position based on the previous study result. And here we term that preferred position as adaptive and this random position as non-adaptive. And on the y-axis, we not the total time taken to construct this word. And we find that when we put screen element at their preferred position, they took statistically significantly less amount of time, and the variability was also less in fulfilling the task compared to the non-adaptive version. So with that knowledge in mind, then we went towards making application. So this is a virtual keyboard application. So with virtual keyboard is a very well-known field, and there are many examples of virtual keyboard, but we couldn't make any of them usable by them because traditionally all virtual keyboard, they follow this left to right and top to bottom pattern, and they also do not have a minimum spacing among screen elements. So these users, they cannot use this virtual keyboard. And later on, we also worked with a famous professor at IISc itself. He unfortunately was diagnosed with ALS on his when he was in mid 70s. And we found a similar reproduction of results, that when we put all 26 keys on the keyboard, he found it cannot click buttons on that. So we divided the buttons into two screens based on, there was a bit of mathematics. So if you we may consider the mathematics in a later AI lecture, or you can also check the state space search lecture. We used a genetic algorithm to optimize the screen layout, and now we are also working with Indian language keyboard. And again, we found that by making this two screen arrangement, the keyboard became accessible to them. And then we extended the keyboard interface into chat message interface, in which instead of uttering out the word or sentence, they can send this letter as a stored message like a chat to another participants. And we tested it with a bunch of users there. And we also developed, this is slightly older application, in which we constructed multiple user interface. So here the user trial, I recorded the video with me only. And in this system, we developed multiple user interface for the same ASC application. That means constructing correct grammatical words from by choosing a set of letters in various way. In one case, it took help from natural language generation techniques and conducted a sort of interview with user based on the thematic roles, like say who, when, what, like it asked this sequence of questions to the participant, and based on the answer, it automatically creates a grammatically correct sentence. And in a later part, we use this type of stored message interface and uh, interface with only words, no pictures, and so on. And the same interface can gradually be optimized or adapted as a person grows up and his needs keep on changing. And one of our research staff, Kamal, he also developed a browser interface for our professor. And again, we follow the similar design guidelines, that keeping the top left portion of the screen empty and putting the screen elements at the middle of the screen. And again, he found this useful, and he rather is still using it, the same interface. And we are kind of now doing a we are kind of working with him to further modify the user interface. So this is, he was checking his emails. And we are talking about IES tracker. So we already set up two commercial IES tracker and computing system at Vidyasagar, but then we thought that to scale it up, we cannot ask everyone to buy eye tracker. So rather we developed computer vision algorithms using machine learning, by which a webcam can be used as IES tracker. The problem was that we have to even limit the number of screen elements, because the webcam guess eye tracker was not as accurate as the commercial eye guess trackers. But it still had some applications, like here you can see for multiple choice of questions, they can use or they are odd line exam, they can use that. And then we also experimented with this human robot interface, by which we again following the similar design philosophy, by bigger buttons with adequate spacing, inter-element spacing among buttons, we could make them do this simple pick and drop task using a video see-through interface. So in this particular case, we are using a commercial eye gaze tracker, but later on, we also experimented with a webcam-based gaze tracker. So these are some functionalities that it can follow a blue object. We will later on we will have a separate lecture on human-robot interaction. But here we tried to help their rehabilitation process because many of these users, young adults who are say already finished their coursework, they were trying to do something like a fabric printing task, which you can probably seeing in the screen now, that had they are trying to create some prints on a piece of cloth with the help of a well-bodied user, and the work was pretty boring for both the person who is the person with disability as well as their able-bodied helping hand, because the work was very repetitive. So we tried to train the robot to do that, and we undertake two studies using this robot. One is that whether they can bring the robotic arm at any place within a in a 2D plane within this robot's working envelope, and the second task was whether they can pick and drop an object using the robotic arm. And all the users, around 8 to 9 users that we worked with, they could do this task, although they took longer time than their able-bodied counterpart. And in this particular one, the study was conducted in last January, and we used a webcam instead of a eye gaze tracker. And then similar type of um, user interface can also be extended for other cyber physical systems. So here again, the aim is to um, help them to manipulate physical object like a normal kid do, that they play with car. This is just a toy RC car, and then we make some embodiment by which we can control this toy RC car using eye gaze tracking or other modalities. So here we are controlling the RC car using simple computer vision technology that we designate one of the targets and it is moving towards. So here we are again moving towards more cyber physical system than our earlier talk on assistive technology. But again, the aim is to enable this user to play with physical object like their able-bodied counterparts. And then we undertook a short study with a different school in Bangalore for students with learning disabilities. And here also we took the approach that we didn't provide any software solution. Rather, we collected their eye gaze pattern when they are reading a text, and found that analyzing eye gaze tracker, we can detect early signs of dyslexia, mostly by the analyzing the fixation patterns and the right to left or the regression type of saccadic gaze movement. That means when they are reading a English text, persons with learning disability often has a reverse eye gaze movement from right to left. And by detecting that in real time, we can diagnose early signs of learning disability. So this was like just a short study, and we are now planning to extend this study. So finally, in conclusion, we are not only working on providing this software solution. Of course, we got affected with this existing COVID-19 related lockdown, and we cannot uh, develop new technology for this user, or rather we cannot test these technologies with this user. But we are still working with the famous professor in our institute, who is kindly testing and sharing video of many of our technology when he is actually interacting with them. So that work is still going on. But in parallel, I am trying to develop new standards, or more specifically, recommendation from the telecom branch of UNO, the International Telecommunication Union. And again, the uh, aim is same, that instead of develop pinpoint technology, that something for blind, something for motor impaired, rather if we can personalize user interface, which can include users with a wide range of abilities, and considering the same the user who we are diagnosing with say motor impairment, that person may also have visual impairment, and similarly the person whom we are marking as visually impaired, he may also have some may need some support on the cognitive ability. So instead of categorizing persons with respect to their impairment, which is also kind of offensive to the end users themselves, rather developing technology which can personalize user interface to include a wider population. So with that, I will stop talking. Again, thanks for your time.